Math 3 Lesson Summary Video. Winner, winner. This lesson is a develop understanding task, which is meant to introduce you to a concept, but not necessarily finalize rules or strategies. The purpose of this lesson is to introduce rational functions and asymptotic behavior, as well as identify the key features of the rational function. Imagine that you won the lottery and were given one big pot of money. Of course, you would want to share the money with friends and family. If you split the money evenly between yourselves and one friend, what would be each person's share of the prize money? This situation is getting you to think about dividing up a whole. And so when we think about it, if we have one whole lottery, if there are two of us, we'll divide it by 2. So that would be 1/2. If there are 3 of us, we would divide it by 3, 1/3. If we were to model this situation using our multiple representations, so we'll need tables, equations, graphs. If I think about that equation, I'm taking the one whole and I'm dividing it by however many winners or however many people there are. So my equation would be f of x is equal to 1 divided by x, with x being the number of people that will be sharing the prize. If I make my table for that, I will have 1, if I only have one winner, well, there's only one prize. 1 divided by 1 is 1. 2 winners, each of us get half the prize. 3 winners, 1/3 of the prize. 4 winners, 1/4 of the prize. 5 winners, 1/5 of the prize, so forth and so on. If I were to graph this, I just need to go in and put my points. So I have 1 person, we get the whole shebang, 1 whole prize. If there are 2 people, well, then we get half of the prize. 3 people is 1/3, that's roughly 0.33, so that would be about right here. 1/4 is 0.25, so that would be right here. 1/5 is 0.2. All right, and then 1/6, right about there. So if we take all of our pieces and connect them into a continuous graph, we might get something that looks like this. Now, what the next section of the task is having you to look at is what happens if you actually switch the domain and range. Now, we know from previous units it's called an inverse. So if we're going to switch the domain and range, what actually happens to the graph, what actually happens to the table, so forth and so on. And what's interesting about this particular function is that when you do graph the inverse, the switch of the x and the y, you actually get the same thing. Now this is because if you look at this original graph, it's symmetric about the line y equals x. So when you reflect it over the line y equals x, which is what happens when you take the inverse, you get the same thing. So it is symmetric about the line y equals x, which is a very interesting characteristic of this graph. As you move on through the rest of the unit, what we're going to be looking at are characteristics of the rational function itself. So if we look at the graph, here's the equation of the basic parent rational function. If we look at the graph, things that we may notice is that we have symmetry. We just mentioned symmetry over y equals x, but we also have symmetry over y equals -x. We can fold it over this diagonal as well, and it is symmetric. We have rotational symmetry. About the origin, we can rotate it 180 degrees, and it will be equal to itself. It's a very symmetric kind of function. If we look for key features, first key feature, domain and range. Domain, it looks like it continues on for all of the x values except 0. Right here, it never equals 0. Now, if we think about that from the standpoint of the equation, if we look at the equation, what you'll notice is the reason that x can't be 0 is x is in the denominator. We can't divide by 0. So our domain is going to be all of the numbers except for 0. We have to leave 0 out. When we look at the range, the graph kind of looks the same for the y values. It goes all the way close to 0, but it never quite touches 0. If we look at the equation again, the reason for this is going to be if I take 1 and divide it by anything, I'm never going to get 0. The only way I can get 0 with division is if I take 0 and divide it by something. But if I take 1 and divide it by anything, it's still technically going to be something. Might be a really little bit of something, but it's not going to be 0. So my input is not allowed to be 0 because I can't divide by 0. And my output is just never going to turn out to be 0 since 0 is not involved in any way. So that means that our domain and our range both turn out to be all of the numbers except for 0. Notice in interval notation, to show that, I take all the numbers less than 0, but notice I didn't include 0. And then I take all the numbers greater than 0, yet again not including 0, and then we just use the union to put them both together and say this and this, these together make up the domain and the range for this function. Next key feature would be our intervals of increase and decrease. Remember, intervals of increase and decrease are one of the key features that we look for. If I start at the left, this is getting ever so slightly lower, ever so slightly, and then when we reach this corner, it just like drops off the cliff. When we come up here, we're going down very steeply, and then we kind of even off. But we're going down the entire time. At no point are we going up. It kind of looks like you go up at 0, but remember the function doesn't exist at 0. So there's nothing going on at 0. On this side, it's going down the whole time, and on this side, it's going down the whole time. So when we talk about our intervals of increase and decrease, there are no intervals of increase. It's never increasing from left to right, and it's decreasing on all of the intervals that it exists on. X-intercepts and y-intercepts. Well, we have already determined that there is no domain and range at 0, which means there are no points at 0, which means there are no x-intercepts and y-intercepts. And since it's decreasing, 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 and it's covering all of the numbers in the domain and range except for 0, there are no minimum and maximum. We don't have any relative minimums, relative maximums, turning points, stuff like that. So we have no minimums and maximums. And then our end behavior. Let's look at these ends over here. So as we're going to the left, it's not going to infinity. Look where the y value is getting closer and closer and closer to. As we go to the left, it's getting closer to 0. And as we go to the right, same thing. It's not going off to infinity. It's actually leveling out on either side. So we actually have end behavior that is a number. So our end behavior, as x is approaching the left, negative infinity, f of x is approaching 0. And as x is approaching positive infinity, the right, then f of x is also approaching 0. Because this is the case, this gives us some very special pieces to our graph, which we have used in other graphs, exponentials in particular, and that is asymptotes. In fact, we have two asymptotes. We have a vertical asymptote that's resting right here on the y-axis that's keeping our domain from equaling 0. That's the restriction. We can't divide by 0. So we've basically got a wall here that keeps us from being equal to 0. For our end behavior, because our end behavior, everything is leveling off at 0, we also have this horizontal asymptote here on the x-axis where y equals 0, because y can't be equal to 0. These restrictions in our domain and our range have given us these asymptotes that keep the graph kind of trapped. And so these are the key features for the rational